Cool. All right. Cool. All right. So I lie. Hold on.
It's not very funny.
All right. Anyway, we're going to get started. Today, we're going to be doing our exam review. All right. So I'm going to put down some compounds. We're going to rewind all the way back to when we were talking about solids, and we had these different categories for our solids. All right. So let's try to remember what those were. Can anybody remember a category for our solids? So we got a network solid. What was another one? Metallic. We got two more. Covalent. All right. And actually, they were made up of covalent molecules, but we were careful to call them molecular. And what's the last one? Like sodium chloride, ionic. Cool. All right. So I'm going to put down a few formulas here, and you're going to match them based on one of these four categories. All right, so let's go through and start matching these up here. This zinc, these are all solids, so they all have that solid sort of designation there. Which one of these would zinc be? Metallic. All right. What about the calcium carbonate? That's an ionic compound. C10H12, decane. What do we got? Molecular. And then what about the diamond? Network, right? Network was kind of that very small category. There were only a few specific examples that we had. All right, we said a diamond. Let's just put them all down here so we can remember because there's only three of them. All right, the other one was carbon's other form, which was what? Graphite. All right, and the last one is silicon dioxide, which is what's called quartz. Cool. So we got these different categories here. Which one of these do we think is going to have the highest melting point? Which one of these would we have to heat the most before we could get it to turn into a liquid? The network, right? So this has our highest melting point. And the other two, there are two others up here that are also quite high in terms of melting point, and those are our ionic. All right. And then which one's our low melting point one? Actually, that one's going to be the easiest one to pick out. Metallic or molecular? Which one is our low melting point solids? Molecular. Okay, so out of these high melting point solids here, which one is the most brittle, the most fragile? Like if I took a hammer and smashed it with it, it would just explode into a million pieces. The ionic, right? So these are what we call brittle or break under force. What happens when we hit a metal with a hammer? It'll dent, right? So this is what we call a malleable solid. That's why it's very convenient to make tools out of. And then our absolute strongest solid that we have are those network solids. Cool. All right. So now let's take a look at a few molecular solids. So all of these are going to be molecular. Well, actually, we'll move on to liquids. They don't have to be solids anymore. All right, so now we're going to look at, remember, if you're in the liquid state at like room temperature, you're definitely going to be a covalent compound. Those metals, those ionic compounds, and those network solids all have extremely high melting points, way higher than you will ever encounter, right? So when we're talking about liquids here, we're talking about molecular compounds. So let's take a look at a few here. All right, starting to look like an organic chemistry class. All these structures. Cool. All right. So what we want to do is we want to take these three structures. I'll give you a minute to copy these down here. But what we want to do is we want to start thinking about the intermolecular forces that these will have with neighboring molecules of the same type. All right. So what I want to know is what is the strongest IMF in each of these molecules, or rather that they have between neighbors. Oh my gosh. Got a chemistry disaster there. I had a carbon with 5 bonds. All right, my bad. So, not really a huge deal at all, but just note that this hydrogen should not be there. My bad. All right, so we were talking about these intermolecular forces. These are these interactions that molecules have with neighboring molecules. What was the strongest of the intermolecular forces that we discussed? Hydrogen bonding. Whoops. And which one of these has hydrogen bonding available to it? B. All right. And what is it about this structure in B that lets me know that it can hydrogen bond? The OH right here. Boom. Right. Remember, in order to hydrogen bond, you have to be one of 3 special bonds: fluorine hydrogen, oxygen hydrogen, and nitrogen hydrogen, right? All sitting next to each other on the periodic table, all of our teeny tiny and very electronegative atoms. All right, because of that, because they're teeny tiny and very electronegative, they can form these really strong intermolecular interactions called hydrogen bonds. And what was the very weakest type of intermolecular force that we discussed? Dispersion forces. And so which one of these only has dispersion forces available to it? C. All right, remember carbon and hydrogen have the same electronegativity, basically the same dispersion, same electronegativity. So those bonds are not polar. There are no polar bonds in this molecule. And those non-polar molecules only have dispersion forces available. All right, so then what's the one that we haven't discussed? Dipole-dipole. And what is it about this structure here that lets me know it can dipole-dipole interact? We got this polar bond between carbon and oxygen, right? Oxygen's right next to fluorine, very electronegative. Carbon's a few away. It's not quite as electronegative. So this is going to be this polar bond, and polar bonds can interact through dipole-dipole interactions. Right? Which is, remember, if we have, and again, we're talking about interactions between neighbors. So really a better way to kind of picture this would be to draw two of these molecules. All right, and remember, they're going to line themselves up in such a way that that partial positive end of one molecule, right? Carbon here has this partial positive charge, and that's because oxygen has stolen all of its electron density because it's more electronegative, right? Remember, electronegativity, this tug of war over electrons. And then the same thing is going to be true in our other molecule here. My oxygen has this partial negative charge, and my carbon has this partial positive charge. And the oxygen of one molecule is talking to or interacting to the partial positive carbon of its neighbor, right? So this right here is my dipole-dipole interaction. Cool. All right. So one of the other things that we covered at the very beginning was this calorimetry. All right, so we were introduced to this equation. Q equals HC times M times delta T. All right, go through and label the variables in this equation for me. What is what here? All right, what does the Q stand for in this equation? It's energy, yeah. And so specifically thermal energy, or what we just call heat. But absolutely very important to think about it as an energy and remember that it's going to be in units of energy, joules, kilojoules, calories, something like that. What's the HC? Yeah, heat capacity or specific heat capacity or just specific heat. Nobody calls it the same thing, but yes, it is the specific heat capacity. All right, and remember that specific heat capacity is unique to a particular material, so depending on what you have, you're going to look it up on that table. What is the M in this equation? Mass. And the delta T? Change in temp. All right, and what are we going to remember for our delta T? What minus what? Final minus initial. So T final minus T initial. And remember, that could be positive or negative depending on whether your substance is losing thermal energy or gaining thermal energy. Cool. All right. So I will tell you that the heat capacity, actually, do I have the list here? No, whatever. Okay, I will tell you that the heat capacity of aluminum is 0.900 joules per gram degree Celsius. All right. So let's say if 50 grams of aluminum is cooled from 96.5 degrees Celsius to 42.3 degrees Celsius, how much thermal energy, how much heat was absorbed or released? All right, so we got our equation. Q equals HC M delta T. We're going to plug in here our 0.900 joules per gram degree Celsius. Our mass here is 50 grams. And then we have this change in temperature. Do I need to convert my temperature to Kelvin? No, this isn't a gases problem, so we don't have to worry about that. And we can always check because of our units are given to us here in our problem, right? In our specific heat capacity that we used. Cool. So not going to worry about all that. That's a gases thing. But we are going to take 96.5 and subtract 42.3. No, right? Okay. Remember, final minus initial. Everybody's really wants to take the big number and subtract the little number. Make sure to read your problem carefully. We're ending at a temperature of 42.3 degrees and starting at a temperature of 96.5. All right, so we're going to get a delta T that is negative, and I'm going to punch that into my calculator first so that I keep track of my sig figs. Temperature of negative 54.2 degrees Celsius. All right, that times my 50 grams times my 0.9 gives me a Q of negative 2439. All right, and this is a big number, and everybody's like, oh, that's scary. It's a big number, but why is it a big number here? What is the units on this number? Just in joules, right? And we can see that from our problem. Grams cancel out, degrees Celsius cancels out, so we're left with units of joules. Lastly, we're going to note that we got our 3 sig figs here. So I'm going to report my final answer as negative 2440 joules. Don't forget that 0. You can't chop it off or you change the number. And so was heat absorbed or released by this piece of aluminum here? Released, right? It went down in temperature. So heat was released. Okay, well, where did all that heat go? Well, let's say that when we cooled down this aluminum, we did so by placing it in a water bath. So if the aluminum is cooled in a water bath, and the temperature changes from 23.5 degrees Celsius to what is my temperature going to go up or down? It's going to go up to 27.6 degrees Celsius. Let's ask, what is the mass of water in the bath? And I believe we will need a heat capacity here. Does anybody know what it is for water? Awesome. That's how you know you've done way too many chemistry problems, is when you have stuff like that memorized. But absolutely, the heat capacity for water is that 4.184, again, joules per gram degrees Celsius. Okay, so to be clear, I'm piggybacking off of this previous problem here. You're going to have to use that result from our previous problem. What we solved for was the heat that was lost by that aluminum. All right, and make sure we use our unrounded value in our calculations going forward here. Yeah. The heat that's lost by the aluminum is like necessarily absorbed by the water.
Sorry, the temperature.
Oh, the temperatures. Yeah, we should be good. Yeah, this was a little bit of a messy problem here. Let's just say our temperature changes 4.1 degrees Celsius. Because yes, you're right. They would come to thermal equilibrium. So that should have been that final temperature. I wasn't thinking. All right, so importantly, this problem would have relied on the first law of thermodynamics, which says that energy cannot be lost or created, it can only be transferred, right? So we can summarize that as the amount of heat that is lost plus the amount of heat that is gained equals 0. Oh, remind me later. All right, so in this case, what is it that was losing the heat? The aluminum. So that means the Q of my aluminum plus what was gaining that heat? The water. QH2O equals 0. And I know my Q aluminum here is negative 2439 joules. So plus, what would give me 0? What must that Q of H2O be? Positive 243.9 joules. Okay, so we had to use that first law of thermodynamics to figure out how much heat the water absorbed. And then the heat, the calorimetry of water is going to be governed by that same equation. All right, if we just plug in, I guess let me be good with my sig figs here, plug in that 2439 joules equals 4.184 joules per gram degrees Celsius times mass. This is what I'm solving for here. This is what I don't know. Times that delta T of 4.1 degrees Celsius. How am I going to get mass all by itself? What am I going to have to do algebraically? Move everything else to the other side, right? You want to move everything away from what you're solving for. So I'm going to divide both sides by the 4.184 joules per gram degrees Celsius times 4.1 degrees Celsius. Do that to both sides. We can do anything we want as long as we do it to both sides. All right, and I get that my mass is equal to 142.179. All right, what are my units? Yeah, I'm in mass. So first of all, this all canceled out from this side over here, right? Joules cancel out, degrees Celsius cancels out. I'm left with 1/1 gram, which is the same thing as just grams. All right, and again, being good with my sig fig here, how many sig figs am I going to report to? 2. Limited by that delta T of 4.1. So my final mass, that water bath was about 150 mils or 140 mils, or more specifically in mass, 140 grams. Cool. All right. So we sort of segued from a discussion of heat to a discussion of enthalpy. All right. We had talked about calcium carbonate before. Let me see something real quick. Cool. All right. So calcium carbonate, when you heat it up, all right, actually before it would melt, you wouldn't even get that high of a temperature because this thing starts decomposing into calcium oxide and carbon dioxide. All right, to be clear, what type of reaction category would this be if we're winding back in our minds? I think I already said it. Yeah, decomposition, right? We just got this one reactant, we heat it up, it falls apart into these two components here. That's all well and good for last unit stuff, but for this chapter, what we're particularly interested in is calculating the delta H of this reaction. All right. So we have a balanced chemical equation. I guess let's say that if we didn't have a balanced chemical equation, we would first need to balance it, but you can convince yourself that this is indeed already balanced here. All right. And so what we're going to do is we're going to need to, we'll use for this method, looking up these compounds on our standard enthalpy table. All right. So we're going to bust out that constants page. Here we got calcium section right here. Everybody take a second. You're going to need to grab 2 values from this portion of the table. All right, and which one of these columns am I paying attention to? Just that first one. We'll talk about the other two thermodynamic variables next semester. And which two compounds can we find here? Calcium carbonate. So I'm going to need that 1207.6. And the other one, calcium oxide, negative 634.9. And what are the units on these values that we're grabbing here? Not joules, but kilojoules per mole. All right, I'm also going to need to look up carbon. Let me get rid of all this real quick. Carbon, we need CO2, A, B, C, D. All right, here we go. Okay, again, we only care about that first column. So this is where carbon dioxide gas is. Okay, be careful. We also have a different state of matter, aqueous carbon dioxide. We also have something similar, but not quite what we need, carbon monoxide, right? So just be careful when you're reading your table that you get an exact match. Cool. All right, let me just notate these here with what we just discovered. Whoops. All right, so when we calculate our delta H using those standard enthalpy values, what are we going to chant to ourselves here? Products minus reactants. Cool. So I'm going to take that delta H of the product side, that negative 634.9 plus negative 393.5. And then I'm going to subtract that negative 1207.6. Okay. All right, so punch that into my calculator and I get the delta H of this reaction is equal to positive 179.2. And again, our units for our enthalpy values are in kilojoules per mole. Cool. All right. So what can we do with these enthalpy values that we have here? So first of all, we can say that this reaction is what? Exothermic or endothermic? Endothermic. It's got a positive delta H value. So that calcium carbonate will absorb thermal energy in order to decompose. All right. So the other thing that we could say is we can use this in a stoichiometry problem. So let's say if 4.5 moles of calcium carbonate are decomposed, how much thermal energy is absorbed? How much heat? All right, and how did I know that it was heat that heat was absorbed instead of released? Because it's positive, right? And again, that's what it means to be endothermic, is a reaction that absorbs thermal energy, right? So all of these are kind of saying the same thing. That positive sign out front, endothermic, energy was absorbed, right? All saying the same thing. All right, so I gave it to you in moles here just to make our life a little bit easier. We're going to use that 4.5 moles of calcium carbonate. All right. And then we need to use our delta H value here. Put this down. All right. And remember, we're going to convert this into something that we can use in our math where we split up those units. Same game we've been playing all semester long. The 179.2 kilojoules over 1 mole, but specifically 1 mole of what? Yeah, this chemical reaction as written given this balanced chemical equation up here, right? When you provide your balanced chemical equation, you're saying this is what 1 mole of reaction is. Cool. So then if I'm being really good units wise, I'm not going to just multiply this by that delta H straight away. I'm going to convert 1 mole of calcium carbonate to my 1 molar reaction. So my units are correct. In this case, the reaction's 1-to-1. So if you didn't do it, you would have gotten away with it. But if it's anything other than 1-to-1, that's not the case. All right. And if we start out with these 4.5 moles of calcium carbonate, that means that we're going to absorb 806.4. And those units are kilojoules. And then I'm going to be good and be limited in sig figs by that 4.5 moles. So I'm going to round this to 810 kilojoules of thermal energy is absorbed in this reaction. All right, cool. So we have a chemical reaction here, this decomposition of calcium carbonate, and we can note that one of our products here is carbon dioxide gas, which provides us with a fantastic opportunity to do a gas laws problem. All right, so let's say if we'll stick with that same 4.5 moles of calcium carbonate is consumed or decomposed in this reaction. What volume of CO2 is produced at STP? All right, and the first thing we're going to do is assume that carbon dioxide is an ideal gas under these conditions. Excuse me. Oh, and I will tell you, R 0.082058. All right. So what I do not give you on the exam is that ideal gas law. We got to know that. What is the ideal gas law? PV equals nRT. That we got to know. We rearrange this equation here. We get nRT over P. All right, we're given that value of N in the problem, that 4.5 moles. We always have that value of R from our constants page, but we don't have our temperature and our pressure explicitly given to us. That is this information right here, the STP, standard temperature and pressure. So what is the temperature at STP? Yeah, so it's defined as exactly 0 degrees Celsius, which is 273, which is exactly 273.15 Kelvin. And our pressure at STP is what? Exactly 1 atm. Cool, so we're going to plug in here 4.5 moles times that value for R. Times, let me squeeze it in, 273.15. Divided by that pressure of 1 atm. All right, punch that into my calculator here. And we get a volume of our ideal gas of 100.8 something, 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 636. All right, because of our units for R, moles will cancel out, Kelvin cancels out, ATM cancels out, and I'm left with units of liters. And we're going to round that to 2 sig figs here. So my final volume is just 100 liters, where I indicate that 0 in the middle is significant. Okay, if you could also say 1.0 times 10 squared liters, if you wanted to put it in scientific notation, but you can just put the bar over it. I'm cool with that. Okay. Cool. So the other thing that we can ask is, all right, well, what about the volume if we treat this as a real gas? And this is not an equation that I would expect you to have memorized, so I'm just going to put it down here. All right, now we're going to ask the same question, but we're going to add this correction factor on there. All right, notice how this portion here is just our ideal volume. So ideal plus that correction factor NB will give us our real volume. So first of all, at STP, do we expect this real volume to be really different than our ideal volume? No. So that's why we like the ideal gas laws, because it works pretty well for gases under normal conditions. Unless we crank up the pressure or otherwise concentrate our gas, use a real small volume and a large number of moles, these two should be relatively similar to one another. All right, so at STP, we would expect that we don't really need this real approximation here, but we're still going to do it just for fun. What we do need is that value of B from our table. So let's ignore all this. Let's kind of zoom in. All right, we are talking about carbon dioxide. And we have two values. The first one is that pressure correction factor. What we need is the second value here, our volume correction factor. 0.0427. All right, so this is going to equal that ideal volume plus that 4.5 moles times that value of B, 0.04. What did I say? 27? Yes. All right, if we're being really good, you'll note that the units on these variables are always there to help you square away. So this would be in liters per mole, for example. All right, and so now we have a real volume of 101.0557 liters. And if we round this to the same number of sig figs as our ideal volume, we're still going to just have 100, right? So again, not really worth it to do your real gas approximation around standard temperatures. But if you have a very concentrated gas, all of a sudden it becomes much more important. Cool. All right. Let's look at another chemical reaction here. All right, we're going to look at water. It turns out that if you take electricity and you run it through a sample of water, you will produce hydrogen gas and oxygen gas. All right, everybody take a second and balance this chemical equation for me. All right, so we're going to need a 2 to balance our oxygens, and we'll have to update a 2 on our product side as well. All right, and we want to, again, predict the delta H of this reaction. All right, but now we're going to use a different method to do it. We're going to use these bond dissociation energies. So what I need to do is show you the Lewis structure for these compounds. All right, here's one water molecule. We need 2 of them, though, because of my balanced chemical equation. These are going to decompose into 2 hydrogen gas molecules. Those hydrogen atoms just have that one covalent bond between them. And my oxygen molecule, which has 2 covalent bonds. Or rather, a double bond. All right, so using the table above, you're going to tell me the delta H of this reaction. And when we use this table here, what do we say to ourselves? Does anybody remember? This is not products minus reactants. Broken minus formed, right? And you want to think about it. Remember, we talked about energy. Our reactants are down here. We have to put in energy in order to break bonds. Right? So positive input of energy to break the bonds, and then we get a release of energy when bonds are formed. So that's why it's broken minus formed and not the other way around. We want that minus sign on that release of energy. Cool. All right. So take a second, given this table here, take a second and tell me, predict the delta H of this reaction for me. Oh, my bad. I did not realize how teeny tiny that was to y'all. All right, so given my Lewis structures here, let's identify what bonds are being broken in this chemical reaction. All these OH bonds. Boom. Got to break all four of them. Each one is going to require 463 kilojoules per mole. Cool. And then I'm going to look over on my reactant side, on my product side rather, where I have a bunch of new bonds that were formed in this reaction. What bonds are being formed? My hydrogen-hydrogen bond, and I got two of them that are going to be formed. And then this oxygen-oxygen double bond here. All right, so each one of those hydrogens or hydrogen-hydrogen bonds will require 436 kilojoules. All right, and that oxygen-oxygen double bond, to be clear, we're going to look over here, is going to require not the single bond, right, but the double bond. It's going to require 493, or rather is going to release 495 kilojoules per mole when that bond is formed. Okay, so for my delta H calculation, I'm going to do that 4 times the 463, and then I'm going to subtract, and I'm going to be good and put it in parentheses here, the 2 times the 436 plus the 495. See? All right, so I get a delta H value here of positive 485 kilojoules per mole. So is this reaction endothermic or exothermic? Also endothermic. All right, you got to put energy in order for this reaction to occur. And to be clear, right, we're not really worried about water just falling apart into hydrogen and oxygen on the regular, right? We can pour ourselves a glass of water and it's not just going to decompose. You do have to add energy to it. You can make this reaction happen, but you have to pump a ton of energy into it in order for that to occur. Cool. All right. And so now we have these two gaseous products here. All right, so let's take this same balanced chemical equation here. And we're going to ask ourselves if 2.63 moles of H2O are consumed at STP, what is the partial pressure of hydrogen gas? And what's the total pressure after this reaction is complete? All right, so now we got to use Dalton's laws of partial pressure here in order to figure this out. All right, so how am I supposed to do this here? After this reaction has occurred, I have a mixture of my hydrogen gas. I'm going to picture those molecules with these two black dots. Since it's diatomic, I'm going to be good. And then I have oxygen gas, right? So now we have this mixture of oxygen molecules and hydrogen gas molecules all floating around in the same container. So how do I get the partial pressure of just the hydrogen gas? Well, we're going to assume that these are ideal gases. All right. And so ideal gases, they don't interact with their neighbors. So I don't have to worry about the high oxygen in here to find the partial pressure of the hydrogen. I just need to treat this as an ideal gas and use my ideal gas equation, where the partial pressure of that hydrogen will be the number of moles of hydrogen times R times T over P. All right, so I first have to do some math here. I got to do some stoichiometry. If if 2.63 moles of H2O are consumed, and we have this stoichiometric ratio that tells me there's 2 moles of water consumed for every 2 moles of H2 that are produced. And we have 2.63 moles of hydrogen gas at the end. All right, so now I can use my pressure, and now I can plug in that I have those 2.63 moles of hydrogen times the 82058. All right, and we're at STP, so we have temperature of 273.15 Kelvin and a pressure of 1 atm, of exactly 1 atm. So we're not going to be limited in sig figs by our temperature or pressure. All right, so punch this into my calculator and I get my, hold on. Oh my God. This problem had a fundamental flaw in it, which was the pressure thing. Okay, my bad. Jeez Louise. Fatting 1,000 a day. All right, our temperature, we'll say, is that 273.15 Kelvin, and our volume is 1 liter. You can't have pressure 2 places. My bad. There we go. We'll even say exactly 1 liter. All right, at STP, the pressure would be 1 atm. We can't be at STP here. My units would not have worked out here. So now my units should work out. Moles will cancel out. Kelvin cancels out. Liters cancel out. Cool. So I'm left with my pressure of 58.949 atm. All right, rounded to the correct number of sig figs. If we're going to call that volume exactly 1 liter and our temperature exactly 273.15, we'll have 3 significant figures, or a partial pressure of hydrogen way far away from standard conditions of 58.9 atm. All right, so if I want the total pressure now, there's kind of a few different ways that we could go about it. We could figure out what our partial pressure of oxygen is, and then sum our partial pressures together to get our total pressure. All right, or we can use the fact that the total pressure, kind of the quickest math-wise, is going to be to use the fact that the total pressure is equal to the total number of moles of gas times RT over V. I have my number of moles of hydrogen gas. All right, now that this problem actually makes sense, everybody take a second and see if you can't figure out what the total pressure is in this system. All right, so if I want the total number of moles so that I can use my ideal gas law here, I need the number of moles of H2 plus the number of moles of my other gas in this mixture, the O2. And we already got one of those because we did our calculation before. Okay. If I want to figure out how many moles of oxygen I have, I'm going to need to do the same sort of calculation, but I need to change my mole ratio here. If 2 moles of water are consumed, there's only 1 mole of O2 produced per my balanced chemical equation. All right, or 1.315 moles of O2 with 3 sig figs. Okay, so then my total number of moles here would be what I sum them both up. I'd get 3.945 moles total. And I'm going to be good and mark my sig fig here in that 10th place because this was an addition problem. All right, so then my total pressure is equal to that total number of moles times R. Times that 273.15 Kelvin over my exactly 1 liter vessel. All right, or a total pressure of 88.423 something. ATM. All right, let me begin with my sig figs. I'm limited to those 3 sig figs. All right, so we got a total pressure here. What is the total pressure? We took this route here where we're going to say our total pressure is equal to the total number of moles times RT over V. And we found the total number of moles by summing up the number of moles of our product. We could have gone a different way. It just would have been like an extra step mathematically, which is to say that our total pressure is equal to the sum of our partial pressures, the one that we just calculated for H2, and we'd have to then go in and calculate that partial pressure for oxygen. All right, if you calculated the partial pressure of oxygen, you would again have to have calculated the number of moles of oxygen. So that 1.315 times R times T over V. All right, just for the sake of writing, I'm just going to leave them as variables. If you punch that all into your calculator, you would get a partial pressure of oxygen equal to 29.4745. Which if you added to your initial partial pressure, or rather your initial calculation, your partial pressure of hydrogen, you would get that same total pressure. All right, so you could have chosen 2 different routes here for this problem. equals the 58.949 plus 29.474. Whoop. And you get the same answer. All right, either one of these routes would work because they both use Dalton's law of partial pressures, which tells us that a mixture of these two gases, because they're ideal gases or because we're treating them as ideal gases, they don't have any interactions with one another, and we can just pay attention to each gas separately. Cool. All right, crash course in everything unit 3 here. Okay. Cool. All right. We're going to take our break and then we will start the lab portion of the review here. Cool.